Okay, so over the previous few pages, I broke rank from the textbook to try to show you what it was like if we used rectangles. I used my own notation, that L sub 4, R sub 4, or M sub 4, to try to break you into this idea of width. You have the height, you multiply them together, you add them, and you get it. If you go to the textbook, they start using a lot more of the I's and the N's, and they get really, really deep quick. So hopefully you have conceptually a better idea of what's going on. But now we're going to go back to the textbook, and we're going to look at, okay, we can estimate the area. How do we find the exact area? And the way that we're going to find the exact area is we're going to use something called the limit definition. So let's read through this together. It says, we quickly realized to make our estimation more accurate, we use more rectangles. So you can see there's some error in this first picture using this many rectangles. We'll look in the second picture, there's far more rectangles and there's far less missed area. So remember, we're letting n be the number of rectangles, and delta x was the width, which was the right endpoint minus the left endpoint divided by the number of rectangles. Okay. Again, remember, to find the height of the rectangle, you had to plug in one of the x values in that interval. We plugged in the left endpoints, we plugged in the right endpoints, we plugged in the midpoints, but in all actuality, it doesn't matter which point you plug in as long as it's some point within that interval. So what they call it is, rather than the L sub I or R sub I or M sub I, they just call it X sub I, where X sub I is some point in that interval, right? And so once we found that point in the interval, we plugged it into the function f. This determined the height of each one of these. Okay? GHT, the height of each one of those. And then we multiplied that times delta x, which was the width of every single one of those. So to find the area of an individual rectangle, you did the height times the width. But what did we do then? Then we added all those values together. Well, if you look at adding all those values together, what they use is the summation notation. So if I had n rectangles, I'd find the height times the width, or the area of the first rectangle, and then I'd move on to the second one, and I'd add it, right? And then I'd add it, and then I'd add it, and then I'd add it, all the way to my nth rectangle. So this notation right here, the sum from I equals 1 to n of f of x sub I times delta x, is just the area of each rectangle added together, which is exactly what we did in the chart. So it says the sum from I equals 1 to n of f of x sub I times delta x. That's how you would read that. And then it says, to make this area exact, to be more accurate, what we realized at the top is, to be more accurate, you wanted the number of rectangles to increase. Didn't matter if you used the left endpoint, the right endpoint, or the midpoint. To make it more accurate, sometimes between those it's more accurate, but to be even better and more accurate, you want to increase the number of rectangles. Well, think about what the number of rectangles was. The number of rectangles was the letter n. So we want n here to get bigger and bigger and bigger. So if n is getting bigger and bigger and bigger, we want n to actually approach the number infinity. And this is where limits come in. So remember, this part is the area of the rectangles, and this is really the total area, right? The total area of the rectangles. And this part says use more rectangles. And if the number of rectangles approaches infinity, then your error approaches 0, and you have found the exact area beneath the curve. So it says the definition of the area of a region of a plane. So we no longer have to have a nice circle or triangle or rectangle or square to find the area. We can find the area of any shape. You draw it on the two-dimensional plane. We can find its area by finding the curve, the f of x, the function that estimates the curve, using rectangles to find the area, but then taking those number of rectangles to infinity, using an infinite amount of rectangles to do this. So it says, let f be a continuous and non-negative on this interval. It does matter that we have positive values here. We do want to have our function above the x-axis. So if it's not above the x-axis, just shift it above the x-axis, okay? It says, the area of the region bounded by the graph of f, the x-axis, and the vertical lines x equals a, x equals b. The exact area is the limit as n approaches infinity of the sum from I equals 1 to n of f of c sub I times delta x, okay? Where x sub I minus 1 is less than or equal to c sub I is less than or equal to x sub I, and delta x is b minus a over n. So what the heck did they just say? Don't let it be any more complicated than it was directly right above it. It says, look, f of c sub I would be the height of the rectangle, and it doesn't matter which point you choose in that interval, right, as long as it's between the two endpoints. It could be the left endpoint, the right endpoint, or any point in between. So they use c sub I to say it's any one of those points. So that's the height of the rectangle. Delta x is the width, so multiplying them would be the area of that rectangle. And then you sum up the areas of all n rectangles, and then we're taking the limit as n goes to infinity. Again, all they're saying is delta x here is the right endpoint minus the left endpoint all over the number of rectangles that you choose, okay? So this right here is how we're going to find the exact area. We're going to use the limit as n goes to infinity of that summation, the heights times the widths.